have to learn, these are kind of disciplines in the field of science that you have to learn. That to know when you know and when you don't know, and what it is you know and what it is you don't know. And it's, you got to be very careful not to confuse yourself.
Okay. Now, probably, I don't know about philosophy of Mayas. We have very little information due to the efficiency of the Spanish conquistadores and, well, mostly their priests, who burned all the books. They had hundreds of thousands of books, and there's 3 left, and one of them has this Venus calculations in it. So that's how we know about that. And just imagine our civilization reduced to 3 books. The particular ones left by accident, which ones, see? So, anyway, I get off the subject. I make this up now. What I'm saying now is just a story. Suppose now that the students would discuss, or people would discuss the possible meanings of this. Why? Then they would begin to think about, well, 8 times 365 is 2920. That's got 2 2s in it. Now, 2 is a lucky number, and it has 2 2s in it. And then the 9 represents the god of so-and-so, which is related to Venus, and so forth, and that would be a good argument. Then, but in another city, some other guys getting together would have a different kind of an argument about it. They'd say, look, now, the fact that there's a 20 at the end, if I subtracted that away first, I get 2,900, which is a especially good number from blah, 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 and so on. And they would have different theories. And then someone would come along and say, you know, it doesn't make any difference which one of these theories is right. We still have this fact to go along with. And that is our modern scientific point of view. In the earliest days of science, we got confused arguing philosophically what was a reasonable reason for nature abhorred a vacuum, or it seemed to be nice to, or gods were doing it. There are different kinds of psychological reasons for thinking it probably is all right after you discovered what it was. These things were never useful for predicting what should happen next, and we soon learned not to make these arguments. It's useless. It doesn't add anything. And so we're not going to make my imaginary Mayan arguments about the various gods that make the numbers. And so I'm left, if I'm a modern scientist, with a description of the situation. All right? Now,
there are lots of things that people did. For example, Maxwell put the equations together. The Faraday, he formulated the equations mathematically with some model in his head. And then Dirac got his answer by just writing and guessing an equation. And other people got their answer, like in relativity, got the idea by looking at principles of symmetry. Now, all these methods, and Heisenberg got his quantum mechanics by thinking only talk about the things that you can measure. Now, all of these ideas, we should only talk about things that we can measure. Try to define things in terms of only things you can measure. Or let's formulate the equation mathematically. Or let's guess the equation. Or all these things are tried all the time. Look for symmetries. All that stuff is tried. All that stuff, when we're going against the problem, we do all that. That's very useful. But we all know that. That's what we learn in the physics classes, how to do that. But the new problem, where we're stuck because all those methods don't work. If any of those methods would have worked, we would have gone through there. So when we get stuck in a certain place, it's a place where history will not repeat herself. And that's what makes it even more exciting, because whatever we're going to look at the method and the trick and the way it's going to look is going to be very different than anything that we've seen before, because we've used all the methods from before. Therefore, a thing like the history of the idea is an accident of how things actually happen. And if I want to turn the history around to try to get a new way of looking at it, it doesn't make any difference. I don't care. The only thing that the real test in physics is experiment, and history is fundamentally irrelevant. It has to do with curiosity. It has to do with people wondering what makes something do something. And then to discover that if you try to get answers, that they're related to each other. That things that make the wind make the waves, and the motion of water is like the motion of air, is like the motion of sand. The fact that things have common features turns out more and more universal. What we're looking for is how everything works, and how everything is, what makes everything work. But it's curiosity as to where we are, what we are. It's very much more exciting to discover we're on a ball, half of it sticking upside down. It's spinning around in space. It's a mysterious force which holds us on. It's going around a great big glob of gas that's burning fueled by a fire that's completely different than the fire, any fire we can make. Well, now we can make that fire, nuclear fire. But that's a much more exciting story to many people than the tales which other people used to make up who worried about the universe, that we were living on the back of a turtle or something like that. They were wonderful stories, but the truth is so much more remarkable. And so what's the pleasure in physics is that, to me, is that as it's revealed, the truth is so remarkable, so amazing. And I have this disease, and many other people who have studied far enough to begin to understand a little of how things work are fascinated by it. And this fascination drives them on to such an extent that they've been able to convince governments and so on to keep supporting them in this investigation that the race is making into its own environment. One Sunday, all the kids were all walking in little parties with their fathers in the woods. Then the next Monday, we were playing in a field, and the kid said to me, "Say, what's that bird? What's the name of it? Do you know the name of that bird?" I says, "I haven't the slightest idea." He said, "Well, it's a brown-throated thrush." He says, "Your father doesn't teach you anything." But my father had already taught me about the names of birds. Once we walked and he says, "That's a brown-throated thrush." He says, "Know what the name of that bird is? A brown-throated thrush. In German, it's called a Flügelflögel. In Chinese, it's called a Qinglongtong. In Japanese, a Tohlatohara, and so on. And when you know all the names in every language of that bird, you know nothing, but absolutely nothing about the bird. And then we would go on and talk about the pecking and the feathers. So I had learned already that names don't constitute knowledge. It's knowing the name of something. That's caused me a certain trouble since, because I refuse to learn the name of anything. So when someone comes in and says, "You got any explanation for the Fitz-Clonan experiment?" I says, what's that? He says, "You know, that the long-lived K-meson disintegrates into 2 pies. Oh, yes, now I know. But I never know the names of things. What he forgot to tell me was that knowing the names of things is useful if you want to talk to somebody else." So you tell him what you're talking about.
But the basic principle of knowing about something rather than just knowing its name is something that you stuck to, is it?
Yes, of course. You have to learn. These are kind of disciplines in the field of science that you have to learn. That to know when you know and when you don't know, and what it is you know and what it is you don't know. And it's you got to be very careful not to confuse yourself.
What you're looking at is a very large mass of atoms when you look at a particle that you can see, because a particle you can see even in the microscope is a billion atoms or so. It's a great big thing. But it doesn't stay put because it's being bombarded all this time by the little atoms, and it therefore jiggles a little bit, and that's called Brownian motion. It was discovered by Robert Brown, a biologist, that when he looked through a microscope, he saw this jiggling motion. And being a biologist, you would think that he would decide that this motion that he saw must be a form of life. But he was a good biologist and made the necessary experiments and ultimately discovered that the motion even existed in the water that was enclosed in a quartz crystal that you could get from the ground that had been there for millions and millions of years. And he looked in, it was still jiggling inside there, so he concluded that couldn't be life, that was a universal phenomenon of nature. And it is, that we look very calm, we look at things, they're permanent, they're stationary, but as a matter of fact, of course, they're made out of piles of atoms which are always jiggling. Our eyes can't see the delicate jiggling, but that is a way that you could make a random generator. You could amplify such jiggling. The electrons and wires jiggle too. Everything's jiggling.
The kid said to me, "Say, what's that bird? What's the name of it? Do you know the name of that bird?" I says, "I haven't the slightest idea." He said, "Well, it's a brown-throated thrush." He says, "Your father doesn't teach you anything." But my father had already taught me about the names of birds. Once we walked and he says, "That's a brown-throated thrush." He says, "Know what the name of that bird is? A brown-throated thrush. In German, it's called a Flügelflögel. In Chinese, it's called a Qinglongtong. In Japanese, a Tohlatohara, and so on. And when you know all the names in every language of that bird, you know nothing, but absolutely nothing about the bird. And then we would go on and talk about the pecking and the feathers. So I had learned already that names don't constitute knowledge. It's knowing the name of something. That's caused me a certain trouble since, because I refuse to learn the name of anything. So when someone comes in and says, "You got any explanation for the Fitz-Clonan experiment?" I says, what's that? He says, "You know, that the long-lived K-meson disintegrates into 2 pies. Oh, yes, now I know. But I never know the names of things." What he forgot to tell me was that knowing the names of things is useful if you want to talk to somebody else. So you tell him what you're talking about. When I was a kid, I invented a problem for myself, the sum of the powers of the integers. And in trying to get the formula for it, I developed a certain set of numbers that formula for which I couldn't get. And I discovered later that those were known as the Bernoulli numbers, and discovered in 1739. So I was up to 1739 when I was about 14, you see. And then a little later I discovered something. I'd find out I just invented a thing called, which we now call operator calculus. And that was invented in 1890 something. You see, I was inventing things that came later and later. But the moment when I began to realize that I was now working on something new was when I read about quantum electrodynamics at the time, and I read a book and I learned about it. For example, I read Dirac's book, and he had these problems that nobody knew how to solve. It was described there. I couldn't understand the book very well because I really wasn't up to it. But there, in the last paragraph at the end of the book, it said, some new ideas are here needed. And so there I was. Some new ideas were needed. Okay, so I started to think of new ideas.
This picture of atoms is a beautiful one, that you can keep looking at all kinds of things this way. You see a little drop of water, a tiny drop. And the atoms attract each other. They like to be next to each other. They want as many partners as they can get. Now, the guys that are at the surface have only partners on one side here, in the air on the other side, so they're trying to get in. And you can imagine this team of people, these teeming people, all moving very fast, all trying to have as many partners as possible. And the guys at the edge are very unhappy and nervous, and they keep pounding in, trying to get in, and that makes it a tight ball instead of a flat. And that's what, surface tension, the way when you realize, when you see how sometimes a water drop sits like this on a table, then you start to imagine why it sits like that, because everybody's trying to get into the water. And at the same time, while all this is happening, there are these atoms that are leaving the surface, and the water drop is slowly disappearing. I find myself trying to imagine all kinds of things all the time, and I get a kick out of it, just like a runner gets a kick out of sweating. I get a kick out of thinking about these things. I can't stop. I mean, I could talk forever. If you cooled off the water so the jiggling is less and less, and it jiggles slower and slower, then the atoms get stuck in place. They like to be with their friend. There's a force of attraction, and they get packed together. They're not rolling over each other. They're in a nice pattern, like oranges in a crate, in a nice organized pattern, all just jiggling in place, but not having enough motion to get loose of their own place and to break the structure down. And that's what I'm describing as a solid. It's ice. It has a structure. If you held the atoms at one end in a certain position, all the rest are lined up in a position sticking out, and it's solid at the end. Whereas if you heat that harder, then they begin to get loose and roll all over each other, and that's the liquid. And if you heat that still harder, and they bounce harder, then they simply bounce apart from each other, and they're just individual, I say atoms, there's really little groups of atoms, molecules, which come flying and hit. And although they have a tendency to stick, they're moving too fast. Their hands don't grab, so to speak, as they pass, and they fly apart again. And this is the gas we call steam.
Take any crazy idea. I don't know, it's hard to make up a very crazy one thing, witches or something like that, and you tell about what people used to believe in witches, and of course nobody believes in witches now, and you say, how could they believe in witches? Then you turn around and you say, let's see, what witches do we believe in now? What ceremonies do we do? Every morning we brush our teeth. What is the evidence that the brushing the teeth does us any good in cavities? So you start wondering, are we all, imagine as the Earth turns on the orbit, there's an edge between light and dark. And along that edge, all the people along that edge were doing the same ritual for no good reason. Just like in the Middle Ages, they had other rituals. And you try to picture this perpetual line of toothbrushes going around the Earth. It's to take the world from another point of view. Now, it may well be that brushing teeth is a very good thing because it gets rid of cavities, and you can find out whether it does or it doesn't by trying to find out. Now, you can ask your dentist, and he says, of course. And you say, how about evidence? I have not found the evidence from dentists because they just learned it in school. Now, I'm not trying to argue that it's good or bad to brush teeth. What I'm trying to argue for is to think about things from a new point of view.
It's interesting that some people find science so easy, and others find it kind of dull and difficult. Especially kids, some of them are just eat it up. And I don't know why it is. It's the same perhaps for all subjects. For instance, lots of people love music, and I never could carry a tune. And I lose a great deal of pleasure out of that. And I think people lose a lot of pleasure who find science dull. In the case of science, I think that one of the things that make it very difficult is it takes a lot of imagination. It's very hard to imagine all the crazy things that things really are like. Nothing's really as it seems. We're used to get, hot and cold, and all that hot and cold is the speeds that the atoms are jiggling. If they jiggle more, it corresponds to hotter, and colder is jiggling less. So if you have a bunch of atoms, a cup of coffee or something sitting on a table, and the atoms are jiggling a great deal in the coffee, and they bounce against the cup, and the cup then gets shaking, and the atoms in the cup shake, and they bounce against the saucer, and the heat heats the cup and heats everything else. And hot thing spreads its heat into other things by mere contact, because the atoms that are jiggling a lot in the hot thing shake the ones that are jiggling only a little bit in the cold thing, so that the hot heat, we say, goes into the cold thing. It spreads. But what's spreading is just jiggling and irregular motions, which is easy to kind of understand. It brings up another thing that's kind of curious. That I say that things jiggle, and if you're used to balls bouncing, they slow up and stop after a while. But we have to imagine with the atoms a perfect elasticity. They never lose any energy. Every time they bounce, they keep on bouncing all the time. They don't lose anything. They're perpetually moving. And that the things that happen when we say something loses energy, if a ball comes down and bounces, it shakes irregularly some of the atoms in the floor. And then when it comes up again, it leaves some of those atoms moving, the jiggling. So as it bounces, it's passing its extra energies, its extra motions, to little patches on the floor each time it bounces, and loses a little each time, until it settles down, we say, as if all the motion has stopped. But what's left is the floor is shaking more than it was before, and the atoms in the ball are shaking more than they were before. That the organized motion of all these atoms moving the same way, falling down, and the quiet floor is now transformed into a ball sitting on the ground. But all that motion is still there in a form, or the energy of motion, in the form of the jiggling of the floor, which is a little bit warmer. Unbelievable. But anybody who's hammered a great deal on something knows that it's true, that if you pound something and hit it a lot, you can feel the temperature difference. It heats up. It heats up simply because you're jiggling it. This picture of atoms is a beautiful one, that you can keep looking at all kinds of things this way. You see a little drop of water, a tiny drop, and the atoms attract each other. They like to be next to each other. They want as many partners as they can get. Now, the guys that are at the surface have only partners on one side here, in the air on the other side, so they're trying to get in. And you can imagine this team of people, these teeming people, all moving very fast, all trying to have as many partners as possible. And the guys at the edge are very unhappy and nervous, and they keep pounding in, trying to get in, and that makes it a tight ball instead of a flat. And that's what, surface tension, the way when you realize, when you see how sometimes a water drop sits like this on a table, then you start to imagine why it sits like that, because everybody's trying to get into the water. And at the same time, while all this is happening, there are these atoms that are leaving the surface, and the water drop is slowly disappearing. I find myself trying to imagine all kinds of things all the time, and I get a kick out of it, just like a runner gets a kick out of sweating. I get a kick out of thinking about these things. I can't stop. I mean, I could talk forever. If you cooled off the water so the jiggling is less and less, and it jiggles slower and slower, then the atoms get stuck in place. They like to be with their friend. There's a force of attraction, and they get packed together. They're not rolling over each other. They're in a nice pattern, like oranges in a crate, in a nice organized pattern, all just jiggling in place, but not having enough motion to get loose of their own place and to break the structure down. And that's what I'm describing as a solid. It's ice. It has a structure. If you held the atoms at one end in a certain position, all the rest are lined up in a position sticking out, and it's solid at the end. Whereas if you heat that harder, then they begin to get loose and roll all over each other, and that's the liquid. And if you heat that still hotter and they bounce harder, then they simply bounce apart from each other, and they're just individual, I say atoms, it's really little groups of atoms, molecules, which come flying and hit, and although they have a tendency to stick, they're moving too fast, their hands don't grab, so to speak, as they pass, and they fly apart again. And this is the gas we call steam. You can get all kinds of understanding. When I was a kid with this air, which I was always interested in, I've noticed that when I pumped up my tires in a bicycle, you can learn a lot by having a bicycle. They'd pump up the tires that the pump would get hot. And that also understandable. See, as the pump handle comes down and the atoms are coming up against it and bouncing off, and it's moving in, the ones that are coming off have a bigger speed than the ones that are coming in, so that as it comes down, and each time they collide, it speeds them up. And so they're hotter. When you compress the gas, it heats. And when you pull the piston back out, then atoms which are coming fast at the piston feel a receding or sort of a give. It gives, and it comes out with less energy. It's like going up against something which is soft and yielding. It goes boom, boom, and it loses. So as you pull the piston out and the atoms are hit, they lose their speed and they cool off. And gases cool when they expand. And the fun of it is that all these things which you see or notice in the world about it, the pump heats the gas, or the gas cools when it expands, or the steam evaporates until you cover the cover, and all these things you can understand from these simple pictures. And that's kind of a lot of fun to think about. I don't want to take this stuff seriously. I think we should just have fun imagining it, not worry about. There's no teacher going to ask you questions at the end. Otherwise, it's a horrible subject.
Complicated. It's just a lot of it. And if you'd start at the beginning, which nobody wants to do, I mean, you come in to me now in an interview and you're asking me about the latest discoveries that have been made. Nobody ever asks about a simple, ordinary phenomenon in the street. Oh, like, what about those colors? Or something like that. We have a nice interview and explain all about the colors. Butterfly wings, whole big deal. We don't care about that. We want the big final result. So then it's going to be complicated, because I am at the end of 400 years a very effective method of finding things out about the world. What today do we not consider part of physics, which may ultimately be part of physics? I see. And I realized immediately something. We consider, at the present moment, most people consider that we study the laws of physics, that is how things go, given a certain condition, how the things behave after that. But how did they get into that condition is considered another problem. In other words,
boundary conditions.
Right, boundary conditions. We are given the conditions, the circumstances, and then it evolves from there according to physical laws. We're studying the laws.
Yeah.
It's as though we were doing a chess game again, and we're working on the rules, but we're not worrying about how the pieces are supposed to be set up on the board in the first place. That's not our business. That's the business of history, how the world evolved. Astronomical history, history of cosmology, how the universe exploded or the steady state or whatever it was. It's not our business. It's interesting that in many other sciences there's a historical question, like in geology, the question, how did the Earth evolve to the present condition? In biology, how did the various species evolve to get to be the way they are? But the one field which has not admitted any evolutionary question is physics. Here are the laws, we say. Here are the laws today. How did they get that way in time? We don't even think of it that way. We think of, well, that is that way from forever. It's always been like that, the same laws, and we try to explain the universe that way. So it might turn out that they're not the same all the time, and that there is a historical, evolutionary question.
But how do you see it going? It's hard to speculate. Is it a continuous change, or is it something that depends on big...
You're the speculator, Steve. You and I think differently. I think of the possibilities, but I'm afraid to put things in. When I see the dark, I always think of the dark as too big for me to guess at. To guess, it's not much use in guessing particular things, but you're different, and I would like to discuss with you sometime how do you do that, because I'm really a little afraid to make specific guesses.
Is it your background?
I don't know.
The way you kind of grow up.
I don't know. I'm afraid to make specific guesses, because the moment I'm making that guess, I can see 7 other alternatives. And so, since I see these other alternatives, I don't know which one to piddle with. I don't like to spend a lot of energy on one.
My choice is very simple. I don't set any requirement that the answer be right. It's just what I'm interested to
That's
follow.
the difference. That's the difference. That's the difference.
Yeah.
Well, I'm trying to find
If I'm interested in
I'm trying to find out not how nature could be, but how nature is. See how what's right.
Well, I don't think
you're
you'll ever
interested-
find it, you see. I don't think
Right.
you'll ever find it.
I see. And your idea is to find out what nature could be. Different possibilities.
No.
different
What I think is interesting. Yeah.
even if it's wrong. Best
I mean-
way to progress, I always
Yes.
think maybe, is to try to be as conservative. That's what
Yeah.
Wheeler always said. To try to be as conservative about the physical laws as possible in explaining the phenomenon. And if you continuously fail, then you gradually realize you got to change something. But if you start out by saying got to change something, there's so many ways of changing,
Sure.
and you don't know how it's most likely you don't have to change anything. Most of the time we succeed ultimately in explaining these damn things in terms of the known laws, but it's the cases that fail are the interesting.
The atoms like each other, the different degrees. Oxygen, for instance, in the air would like to be next to carbon, and if they get near each other, they snap together. If they're not too close, though, they repel and they go apart, so they don't know that they could snap together. It's just as if you had a ball that was trying to climb a hill and there was a hole it could go into, like a volcano hole, a deep one. It's rolling along, it doesn't go down in the deep hole, because if it starts to climb the hill and then rolls away again. But if you made it go fast enough, it'll fall into the hole. And so if you have something like wood in oxygen, there's carbon in the wood from a tree, and the oxygen comes and hits it, carbon, but not hard enough. It just goes away again. The air is always coming, nothing's happening. If you can get it faster, by heating it up somehow, somehow, get it started, a few of them come fast, they go over the top, so to speak. They come close enough to the carbon and snap in. And that gives a lot of jiggly motion, which might hit some other atoms, making those go faster, so they can climb up and bump against other carbon atoms, and they jiggle, and they make others jiggle, and you get a terrible catastrophe, which is one after the other. All these things are going faster and faster and snapping in, and the whole thing is changing. That catastrophe is a fire. It's just a way of looking at it, and these things are happening. They perpetual. Once it gets started, it keeps on going. The heat makes the other atoms capable of reaching to make more heat to make other atoms, and so on. So this terrible snapping is producing a lot of jiggling. And if I put, with all that activity of the atoms there, and I put a cup of coffee over that mess of wood that's doing this, it's going to get a lot of jiggling. So that's what the heat of the fire is. And then, of course, if you see, this is what happens when you start to think. You just go on and on. Wonder how did it get started? Why is it that the wood's been sitting around all this time with the oxygen all this time, and it didn't do this earlier or something? Where did I get this from? Well, it came from a tree. And the substance of a tree is carbon. And where did that come from? That comes from the air. It's carbon dioxide from the air. People look at trees and they think it comes out of the ground. That plants grow out of the ground. But if you ask where the substance comes from, you find out, where do they come from? The trees come out of the air? They surely come out of the air. No, they come out of the air. The carbon dioxide in the air goes into the tree, and it changes it, kicking out the oxygen and pushing the oxygen away from the carbon and leaving the carbon substance with water. Water comes out of the ground, you see. Only how did it get in there? It came out of the air, didn't it? It came down from the sky. So in fact, most of a tree, almost all of the tree is out of the ground. I'm sorry, it's out of the air. There's a little bit from the ground, some minerals and so forth. Now, of course, I told you the oxygen, we know the oxygen and carbon stick together very tight. How is it the tree is so smart as to manage to take the carbon dioxide, which is the carbon oxygen nicely combined, and undo that so easy? Ah, life. Life has some mysterious force. No, the sun is shining. And it's the sunlight that comes down and knocks this oxygen away from the carbon. So it takes sunlight to get the plant to work. And so the sun, all the time, is doing the work of separating the oxygen away from the carbon. The oxygen is some kind of terrible byproduct, which it spits back into the air, and leaving the carbon and water and stuff to make the substance of the tree. Then when we take the substance of the tree and stick it in the fireplace, and there's all the oxygen made by these trees, and all the carbon would much prefer to be close together again. And once you let the heat to get it started, it continues, and makes an awful lot of activity while it's going back together again. And all this nice light and everything comes out, and everything is being undone. You're going back from carbon and oxygen back to carbon dioxide. And the light and heat that's coming out, that's the light and heat of the sun that went in. So it's sort of stored sun that's coming out when you burn a log. Next question, how is it the sun is so jiggly, so hot? I gotta stop somewhere. I'll leave you something to imagine. Most elastic things like steel springs and so on is nothing but this electrical thing pulling back. You pull the atoms a little bit apart when you bend something, and then they try to come back together again. But rubber bands work on a different principle. There's some long molecules like chains, and other little ones that are shaking all the time, that are bombarding them, these chains. And the chains are all kind of kinky and knocked about and shake. When you pull open the rubber band, the strings get straighter. But these strings are being bombarded on the side by these other atoms trying to shorten them by kinking them. So it pulls back. It's trying to pull back, and it's pulling back only because of the heat. So if you heat a rubber band, it'll pull more strongly. For instance, if you hang a weight with a rubber band and put a little match to it, it's kind of fun to watch it rise the way it heats more. And there's another thing you can check that this idea is right, that it's heat that drives a rubber band. If you pull the band out, just like when we push the piston in the gas, if you pull the band out, the tightening string hitting those molecules makes them move faster, and so it's warmer. And if you take the band and let it in, then the molecules hitting the strings, which sort of give as the thing hits, they give in to the soft like, and they lose energy when they hit these retiring strings. So it cools. And there is a little way you can do this. You're not very sensitive. It's a small effect. And if you take a fairly wide rubber band and put it between your lips and pull it out, you'll certainly notice it's hotter. And if you then hold it out and let it in, you'll notice it's cooler. At least you'll notice a certain difference in what happens when you expand it, when you contract it. And I've always found rubber bands fascinating, to think that when they're sitting on an old package of papers for a long time, holding those papers together, it's done by a perpetual pounding of the atoms against these chains to hold it, trying to kink them year after year. Well, rubber bands don't last that long, but anyhow, for a long time, trying to hold this whole thing together. The world is a dynamic mess of jiggling things if you look at it right. And if you magnify it, you can hardly see anything anymore because everything's jiggling and they're all in patterns and they're all lots of little balls. And it's lucky that we have such a large scale view of everything that we can see them as things without having to worry about all these little atoms all the time.
The world is strange. The whole universe is very strange. But see, when you look at the details and you find out that the rules are very simple of the game, the mechanical rules by which you can figure out exactly what's going to happen when the situation is simple. It's again this chess game business. If you were in just a corner where only a few pieces are involved, you can work out exactly what should happen. And you can always do that when there's only a few pieces. And so you know you understand it. And yet, in the real game, it's so many pieces you can't figure out what's going to happen. So there was a kind of hierarchy of different complexities. It's hard to believe. It's incredible. In fact, most people don't believe that the behavior of, say, me, one yak, and you nodding and all this stuff is the result of lots and lots of atoms all obeying these very simple rules. Come out that it evolves into such a creature that the billion years of life with its experiences has produced a thing with prongs that stick out like this and so on. There's such a lot in the world, there's so much distance between the fundamental rules and the final phenomena that it's almost unbelievable that the final variety of phenomena can come from such a steady operation of such simple rules.
In science, to give all the answers to the wonderful questions about what we are, where we're going, what the meaning of the universe is, and so on, then I think you could easily become disillusioned and then look for some mystic answer to these problems. We're exploring, we're trying to find out as much as we can about the world. People say to me, are you looking for the ultimate laws of physics? No, I'm not. I'm just looking to find out more about the world. And if it turns out there is a simple ultimate law that explains everything, so be it. That would be very nice to discover. If it turns out it's like an onion with millions of layers and we're just sick and tired of looking at the layers, then that's the way it is. But whatever way it comes out, its nature is there and she's going to come out the way she is. And therefore, when we go to investigate it, we shouldn't pre-decide what it is we're trying to do except to find out more about it. And so altogether, I can't believe the special stories that have been made up about our relationship to the universe at large, because they seem to be too local, too provincial. The earth, he came to the earth. One of the aspects of God came to the earth, mind you. And look at what's out there. How can it isn't in proportion. It also, another thing, has to do with the question of how do you find out if something's true? And if you have all these theories of the different religions, have all different theories about the thing, then you begin to wonder. Once you start doubting, which I think to me is a very fundamental part of my soul, is to doubt and to ask. And when you doubt and ask, it gets a little harder to believe. I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong. I have approximate answers and possible beliefs and different degrees of certainty about different things, but I'm not absolutely sure of anything, and there are many things I don't know anything about. But I don't have to know an answer. I don't feel frightened by not knowing things, by being lost in the mysterious universe without having any purpose, which is the way it really is as far as I can tell, possibly. It doesn't frighten me. We're exploring, we're trying to find out as much as we can about the world. People say to me, are you looking for the ultimate laws of physics? No, I'm not. I'm just looking to find out more about the world. And if it turns out there is a simple ultimate law that explains everything, so be it. That would be very nice to discover. If it turns out it's like an onion with millions of layers and we're just sick and tired of looking at the layers, then that's the way it is. But whatever way it comes out, its nature is there and she's going to come out the way she is. And therefore, when we go to investigate it, we shouldn't pre-decide what it is we're trying to do except to find out more about it. And so altogether, I can't believe the special stories that have been made up about our relationship to the universe at large, because they seem to be too local, too provincial. The earth, he came to the earth. One of the aspects of God came to the earth, mind you. And look at what's out there. How can it isn't in proportion. It also, another thing, has to do with the question of how do you find out if something's true? And if you have all these theories of the different religions, have all different theories about the thing, then you begin to wonder. Once you start doubting, which I think to me is a very fundamental part of my soul, is to doubt and to ask. And when you doubt and ask, it gets a little harder to believe. I can live with doubt and uncertainty and not knowing. I think it's much more interesting to live not knowing than to have answers which might be wrong. I have approximate answers and possible beliefs and different degrees of certainty about different things, but I'm not absolutely sure of anything, and there are many things I don't know anything about. But I don't have to know an answer. I don't feel frightened by not knowing things, by being lost in the mysterious universe without having any purpose, which is the way it really is as far as I can tell, possibly. It doesn't frighten me.
But take the Mayan Indians. They had a writing system, and we know some of the things they wrote were astronomical things, and they had a scheme for predicting many things in the sky, eclipses and so on. And let's take the example of when Venus, which was important to them because it represented evil of some sort, was a morning star and when it was an evening star. So they could predict ahead of time whether this bad influence was going to be in the morning or in the evening. And so they discovered that if they waited, that this cycle of morning, evening, morning, evening, morning, evening, 5 of those occupied just exactly the same time, as 8 times a certain period that was important to them, 365 days. It's not exactly a year, and they knew the difference, but they still counted in 365-day intervals, which they called a tune. So they said that 5 of these cycles is 8 tunes. Then they discovered, of course, very quickly that if they did this 5-cycle bit for 8 tunes 10 times, they were off by about 6 days. And so they had a rule for shifting, making corrections as they went along, and thus had a very good way to predict when Venus was coming up. Okay? Now let's look at this thing from a point of view. Suppose that the professors, the priests in those days, who wrote this stuff and taught their students these rules, were giving a lecture to try to explain what they did in order to make these wonderful predictions about Venus. Then, if the fellow was any good at exposition and really knew what he was doing, he would say, what we're doing is we're counting the days, just like you're putting nuts in a pot. And we keep on counting 365 nuts, and then another 365, and another 365, and another 365. The guy says, what a lot of work. And we get all finished, we say, that's 5 of these periods. Now they understood what he said. That's easy. They did not know a quick and tricky way to add 365 times 8. I'm sorry, I said 5 times, I meant 8 times. The students were learning in the meantime the laws of arithmetic, something which is to us now, because we have public and free general education, almost everybody has to struggle through and learn how to add numbers by a tricky scheme of writing them in place system and making carryings and so on, so that if you buy wine for $4.15 and your meal is $2.87 or vice versa, it costs $7.02. And the girl who does this, the waitress, just an ordinary person, in 2 minutes does that. How did she do it? What is she doing when she's adding $4.15 to $2.87? She's doing this, counting out 415 pennies, then counting out 287 more pennies, and telling you how many pennies you would have got if you counted them all from the beginning to the end. But it's highly educated and very trained to be able to do that with those large numbers quickly. This training is something, in spite of the fact that everybody's got it. It's something pretty good, because in the 14th century, mathematicians they were called who could do that. Almost everybody in our civilization can do that, but I took this example, you can understand what's involved. What the students are taught, you see, in our particular problems now about physics, there are many bigger numbers. The numbers are much bigger. It's hard, the numbers are so enormous you can't count them directly. And so we've invented a fantastic array of tricks and gimmicks for putting together the numbers, adding, counting, checking, and so forth, without actually doing it the way I could describe what we're trying to do. If I say, I draw this and I draw that and I draw this and I draw that and I see where the end point is, we don't actually sit down and draw 7,000 arrows and find out where the end point. We have a way of figuring out where it'll come, just like we don't actually count 415 pennies and 287 pennies to find out that you owe me 702 pennies. We do it by another trick. These are the tricks of mathematics, and that's all. So that's the part I'm not going to worry about. We're not going to worry about that. So they'll relax. You don't have to know mathematics. All you have to know is what it is. All it is tricky ways of doing something which would be laborious otherwise. So it's true that in the years we have developed enormous abilities in mathematics, and it takes a long time to train the students, and so therefore they're very highly educated in that. But if you ask them why, now we go back to the Mayans, we ask them why the rule. Why, when you fill up a tub 8 times with 365 day markers, it comes out that the Venus is up 5 times. They don't know. They don't understand it at all. The more accurately they can do it, the fact that they know that they have to change it by 6 days and so forth, adds nothing to their understanding of it. The student who has learned all this mathematics and is able to make these calculations, not only of Venus, of the Mars, the Sun, the eclipses and everything else, is a super priest, doesn't know why any better. And if he would explain it's nothing but counting days, he would be reduced to the truth on the one hand, and to an honest statement that he doesn't understand it. On the other hand, and he could tell somebody all about it who doesn't know how to count all these numbers so trickily and so cleverly as this priest students knew, okay? Now, probably, I don't know about philosophy of Mayas. We have very little information due to the efficiency of the Spanish conquistadores and, well, mostly their priests, who burned all the books. They had hundreds of thousands of books, and there's 3 left, and one of them has this Venus calculations in it. So that's how we know about that. And just imagine our civilization reduced to 3 books. The particular ones left by accident, which ones, see? So, anyway, I get off the subject. I make this up now. What I'm saying now is just a story. Suppose now that the students would discuss, or people would discuss the possible meanings of this. Why? Then they would begin to think about, well, 8 times 365 is 2920. That's got 2 2s in it. Now, 2 is a lucky number, and it has 2 2s.